Hello, everyone. Thank you for joining. I'll just give it another sort of minute and then we'll kick off the webinar, if that's all right. So just let people in through the lobby and things. As I say, we'll give it another minute and then we'll start so we can keep reasonably to time. Right, I think I'll start because we're 2 or 3 minutes past the hour. So hi everyone and welcome. I'm Duncan Wargoose. For those that don't know me, I'm BDM Head of Treatment at Xylem UK and Ireland. And thanks for joining us today. In this brief session, we're going to be focusing on how to maximise existing assets to meet tight phosphorus limits and support growth using innovative ballasted clarification technologies that we have. The session's going to run for about 25 to 30 minutes. We've got a couple of quick polls where we'd really love your input, I would. And in the second half, we'll open things up for questions. You're currently in listen-only mode, and hopefully you are able to hear me. And we are recording this session to share. So some of the key objectives of today's session is to review the challenges of phosphorus removal. What are they right now? Understand some of the available treatment strategies, gain insight into ballasted clarification technology particularly, and then follow that up with some review of some UK case studies and where it's successful implementation and how it's been utilised so far. Before I get started in earnest, I'd just like to remind everyone, encourage you to get involved and ask any questions. There's a Q&A function. The chat function is disabled, but the Q&A function is there. Please use it. Send your questions in throughout the session. And those that cannot stay for the full duration, don't worry. We can share a recap of the content and we're recording the session to be available on demand and shared with everyone afterwards and anyone else who wants to look at it. Okay, just a couple of very brief slides about Xylem. Some of you might not appreciate who Xylem is, might not be a name fully familiar. So Xylem's a global leader in the sort of water solutions sector, and environmental sector. We're committed to sort of empowering our customers and supporting communities to build a more water secure world globally. Whether that's with utilities, industrial companies, or private or commercial customers and clients. There's more than 23,000 colleagues in the business across over 500 locations across 150 countries in the world. So we're a Fortune 500 company on the New York Stock Exchange, and just in terms of scale, we turned over about $8 billion last year. This slide I always like, it gives a bit of a historical context to who Xylem are, and we're basically a heritage. Although Xylem's only founded in 2011 as its own entity, some of the brands you'll be familiar with there have been around since the earliest one of Gould's 1848 and have their own heritage. So they're trusted brands like Flight, Sanitaire, YSI, Wedeco, among others, and some of the more recent sort of partners and companies we've acquired like Centus and Evoqua have accelerated our own transformation to provide sort of advanced technology solutions for the sector. So Xylem is now one of the leading water technology providers in the environmental sector. So hopefully that gives you a bit of context of where Xylem sit and some of the brands associated and what sits behind us that you may be more familiar with. So moving on to the webinar in earnest, this is a slide sort of picking up on some of the key areas from AMP8 that you'll probably recognise that are real challenges. One of them, the first box, is around increasing treatment capacity and ensuring we have FFT available. And that sort of links to the third box on storm overflows. By ensuring we treat all we can, and more potentially, we can help to minimize the number of spills in the network. And that's a key part of it. And then the third strand in the middle there, nutrient removal, is particularly a lot of the focus of today in the webinar. And picking up particularly on phosphorus. So, wastewater treatment works have to ensure they meet all incoming wastewater to the regulatory standards, even at peak flow conditions. And that really is a sort of combination of those two. But phosphorus is a key, and we're looking at the Environment Act drives a reduction of total phosphorus to rivers by 50% in 2028. So the water utilities have to balance a number of things, as we know: regulatory requirements, operational efficiency, and financial considerations, while ensuring that the nutrient removal processes that are established are both effective and sustainable. So moving forward, that's been a journey that's involved advanced technologies, effective process management of your existing asset and additional assets, and proper strategic planning. Well, now just like you to join in a bit with a poll, if you could. So the question is, are you actively involved in a pea removal project or planning to start one in the near future? So if you could just very briefly, quickly respond to one of the options. Yes, I'm actively involved. Yes, looking in the near future. No, but have been in the past, or never. That would just give us some context, and myself some context. That would be great if you could submit your answer. Okay, that's great. So looking at the results there, we've got 50% are actively involved, another 23 in the near future, and 12. So majority of either actively now or in the future, or have in the past been involved with pea removal. So that's great to know. Thank you. So pea removal challenges and challenges. With the WINEP programme, which has obviously been in place for the last AMP and the back end of AMP6, it started to become known. We've had an ever increasing drive to remove phosphorus as the key nutrient challenge to river health and environmental health. So that challenge as it got tighter and tighter. So you're seeing much more this AMP. There's a lot of consents that are under 0.3 and below. So there's been a steady move from early consents were at 1, 0.8, 0.7, but as I say, there's been a steady march and an encompassing more treatment works, even down to small flows now and large flows. So that's a key challenge. Another part is utilities needing to, or trying to reduce the amount of build and assets they keep building. So if you can reutilize assets, that's great. Works are already struggling sometimes with capacity, and if you have excessive amounts of backwash, that's part of a tertiary process, that can be a limiting factor. And then the ongoing chemical consumption challenge, which comes with phosphorus removal, where you need to add either a ferric or alum salt to precipitate out your phosphorus. But that's an ongoing cost, an ongoing challenge that needs to be addressed, and trying to minimize that is a key part of the strategy. So some of the available technologies for pea removal. So there's ballasted clarification, which I'll go into a bit more detail, and that's typically from anything from 80 litres a second upwards, and we're talking up to thousands of litres a second. So pile cloth filters typically are fitting in the small end, of which there is multiple sites, up to sort of 100, 150, and then the economics might not stack up against other technologies. We need multiple units. Multimedia filters, again, through to 150 litres a second, and then you need multiple units. Sand filters and deep bed sand filters are a technology that has been used in the past, but is sort of slowly moving out of favour. And then the last one isn't a direct comparison with the other four, but it is an area that we've seen a lot of development and growth. around natrocoagulants and electrocoagulation to help minimize chemical consumption. And they're all key elements. So I just want another quick poll, a bit of help if you can, please. I'd like to know if you've been involved in pea removal projects recently or in the near past or right now. What technologies have you actively come across? Have you come across ballasted clarification, pile cloth filters, multimedia filters, or other? So if you could give us a view, that would be great. And you can tick multiple ticks. So if you've looked at a couple, then please do. Okay. I think that's most people. So what that's telling me from the data is that a third of you have come across pile cloth filters, 20% ballasted clarification, another 30% with multimedia filters, and 20% with others. So quite a spread, which is interesting and useful to know. So some of you have had contact with ballasted clarification in particular. So getting some real insight into ballasted clarification. So there's two parts to the technology we have, and they both use something called magnetite, which I'll talk about in a minute. One is called BioMag, and one is called CoMag, and they have a different purpose. They're sister technologies in the fact they both use magnetite as a ballasting agent. But BioMag is more around increasing and giving the ability to increase treatment capacity within your existing tankage, while also being able to achieve ENR standards without potentially tertiary filtration or tertiary stages. So that leads into the concept that you can reduce costs because you're not having to build lots of new assets. And with that technology, we're treating about 1,000 megalitres per day globally. CoMag is a tertiary process primarily for pea removal, has been the prime drive in the UK and in the US, but also on storm treatment in the US and in Norway, we're building a large plant. And there is a real potential, I think, in the UK, but that does require something work on the legislation to enable that to happen. But you can achieve very tight phosphorus consents with CoMag and ballasted clarification. And one of the key things is you have no backwash water requirements. And the clarifiers ultimately are much, much smaller than conventional, and I'll show that. And we're treating about 2,500 megalitres per day with this technology globally. So the fundamental element that's key to the process for both BioMag and CoMag is magnetite, which is an iron oxide, Fe3O4. Fundamentally, it's the same product, but it's a different grade. So it's an aggregate that's mined. And for BioMag, it uses a smaller grade, about 10 microns, which embeds into the biological floc. So it's that bit smaller. Whereas CoMag is around 50 microns nominal size, and you can have bigger solids particles with the chemical flocs. And hence, the settlement rates with CoMag are much faster in the clarifier stage than with the BioMag. So a bit more about magnetite, which is the key ballast. It's a fully oxidized iron ore, so it's very inert. It's a mined product across multiple, it's available in multiple sources globally. It's not one of these that has only a few countries. In Europe, most of it comes from Sweden and Norway, where they have very large long-term deposits. It's used in a wide range of applications, and water use in this application is quite a small one compared to some of the other industrial applications. But with that, it's relatively inexpensive, and it hasn't moved a lot, even in the last few years when there's been quite a lot of escalation in a lot of things. We're still around the order of 50p per kilo. As I say, it's completely inert. It's got a very dense specific gravity, but one of the key elements is it's very magnetically retrievable. So that links into how it actually gets utilized in CoMag and BioMag technology. We'll talk briefly first about CoMag, which is the tertiary sort of pea removal stroke storm treatment application. And we'll go through a few slides with a bit of detail. So this is an overview. So on the left of the screen, you'll see the influent water comes in, goes through a static mixer where you add the coagulant, and then into what are called your reaction tanks. And typically we have 4 reaction tanks. And in the first 2 tanks, it is mixing, and the basic premise is around 3 minutes per tank of contact time across in the 4 units in the 4 tanks. So as it goes through, once it gets to the 3rd tank, that's where you add the magnetite. And sometimes in the 4th tank at higher flows or peaks, you add polymer to assist with the settlement and bringing it together. And then on the sludge line, you'll see there's the magnetite recovery system and then an inline shear mixer. And I'll talk about that in detail later. So I'll go through how it's applied just to make it a bit clearer, hopefully. So we have coagulant dosed up front into the static mixer, as I said, and then you come into the reaction tanks. If I toggle forward, you'll see we have a sludge recycle loop, and that adds a number of benefits, both in terms of minimizing, helping to reduce the consumption of chemicals, and also to improve the contact time within the system. On the recycle sludge line, you have a waste sludge line, and on that is where the magnetite recovery is fitted. And once you've recovered the magnetite, you return that into tank 3, where your original fresh magnetite was added at the start and is topped up. And then the waste solids is then removed to your standard sludge treatment system. So we get an ability then, by utilizing the magnetite, the clarifiers are much, much smaller if you're not actually utilizing existing humus tanks or other tanks. If you're building new clarifiers specifically, they're much, much smaller, up to 90%. And that's because the rise rates are much, much higher. It settles, basically drops like a stone. You don't have a sludge blanket, as in a conventional final clarifier. So we get around 99% recovery with CoMag, and then the residual goes out in the waste sludge line. So this is a sort of a nice little, very short demo of what's going on, sort of visualizing it if you've never seen one. I know it's showing 3 tanks, but the first tank is usually is split into 2 normally. The 3rd tank is where you add the magnetite, and you can see that happening. I'll just play it again. And that's the recovered magnetite after the mag drum, and then you can see a visualization in the clarifier of the magnetite and the sludge settling, and it is very quick. It just drops. As I say, it's not a conventional idea where you have a sludge blanket with the CoMag system. So where is it applied? It's typically applied in tertiary application, particularly for phosphorus removal, as we talk about. Also on stormwater treatment. We're also been looking at trials on primary treatment and seeing how that can enhance that process. But it's also talking, again, a very big topic for this AMP into the next is about water reuse and water scarcity that we have. There's a number of projects in the RAPID program, and using ballasted clarification up front of UV and ozone on flows is a great method, because one of the benefits of ballasted clarification as opposed to filtration systems is that they're quite tolerant of high solids loading and peaks in the solids loading coming in without getting into a never-ending cycle of backwash challenges. So ballasted clarification typically is much more tolerant of higher solids loadings and peaking in that. BioMag, talk a bit about that now, is applied into activated sludge systems or oxidation ditch, where you apply with a magnetite makeup tank into the activated sludge itself, and then you use the existing final tanks typically to settle out. And then you use the standard RAS circulation system that's already there. And on the waste sludge line, again, you fit your magnetite recovery system to pull that out before your waste sludges then goes off to processing. So with the CoMag, just a brief note I forgot to mention, the recycle rates are something like 5 to 10% of the flow. Okay. So with a BioMag system, what are you doing? So a common problem is you have an existing ASP system of some form. It's operating maybe at 3,000 milligrams per litre or similar, and you have a final tank or a couple, and you've got a flow of Q. You've got a requirement that growth is making you want twice that. Can we just put 2Q through that system? The real challenge often is, well, if you raise the mixed liquors, we're going to get blanket carryover in our clarifiers and failure. They're the bottleneck, the clarifiers. Conventional wisdom would, or approaches over the years has been, well, we'll just increase the capacity by adding additional mirror image of what we've got, and then we'll achieve 2Q. An alternative to that is utilizing something like BioMag. So you dose the BioMag into your activated sludge. By doing that, you can then settle out with the existing clarifiers because you have settlement rates of 2 to 4 meters an hour. So you get a doubling to trebling of your capacity in your clarifier. And by doing that, you can raise the associated mixed liquor in your basin, which gives you the increased treatment capacity available. You reutilize the existing RAS lines. There might be a slight modification to the pumps or a check on that. And then there'll be on the waste sludge line, again, you'll fit your magnetite recovery system before the waste sludge is then taken away. Another little video just giving some sort of impression of the system. So you have a pictorial view there of the silos. That's a typical storage silo. So on larger sites with BioMag or CoMag, you have a silo for the magnetite, which is delivered in air blown in from tankers. And then that's fed into your magnetite makeup tank, you see, which has a mag drum recovery system on top of it. Enters into your activated sludge plant and then through into your clarifiers. This is a short video to demonstrate the improvement in settling that can be achieved with BioMag with comparison against an activated sludge from the same site. So one on the left is a conventional activated sludge, and the one on the right is the activated sludge with some magnetite added to give you an indication of the settling rates and what happens. So just keep your eye on the clock and you'll see how with the additional weight of the BioMag and the density, how it significantly speeds up the settlement. So this is what aids you in overcoming this bottleneck effect on your clarifiers. You can also see from the clarity of the top water level above the sludge and the solids is much clearer, even just after 6.5 minutes there, which affects the improvement of effluent quality that is achieved by BioMag treatment. So one of the fundamental things when looking at BioMag and obviously the reutilization of the final tanks is the analysis of the existing clarifiers. So The fundamental drive is to do a state point analysis to understand your required clarifier surface area and see if they're suitable. So you see on the slide, and that's is obviously a key element of the BioMag design. You have the settling flux curve, you can just see in a light grey, going up, peaking, and then dropping down. And fundamentally, you're looking to achieve a state point linked to your surface overflow rate line that sits below that curve. That's a key element. And a few key things that you look at are, and we happily come to sites, and we do quite often, to do settling tests. We've done over 1,200 settling tests to look at vessel-in coefficients, which is a parameter, just a conventional sort of vessel-in coefficient is often around 6.5 we've seen, and with BioMag you're doubling that typically. But that's a key consideration. So things like the existing sidewall depths are part of it, the slope, and a full analysis. We do a full modelling analysis of the clarifiers to understand their suitability and how much we can actually raise the potential capacity of the system. So, some of the key takeaways: BioMag gives you the opportunity to increase your treatment capacity within the existing tankage between 2 to 3 times. That depends on specifics of the site. And at the same time, you can drive and achieve low ENR standards without tertiary stages. So we typically say we can get down to 0.25 to 0.3 milligrams per litre with BioMag without having to have a tertiary stage in terms of total phosphorus. So that hits quite a lot of sites requirements and a lot of challenges that are there. So that ultimately leads to less capital costs for your upgrades if you're not having to build new assets and groundworks, etc. And typically the BioMag will help improve performance and manage what helps support wet weather flow challenges. I will say it won't solve all your problems. So if you have an activated sludge that is biologically poor and not great before you start, it's not going to suddenly magic and make the biology that much better. There's still the standard biological rigor you have to go through to improve your biology. It gives you some help, but it won't solve it, that challenge, if you have it on the site with poor performing and poor flock formation. I'd just like to do a final poll with you before we go to the next slide and talk a bit about the mag recovery system. So are you involved in projects with capacity increase requirements and growth challenges for a wastewater treatment? It's a very simple question. Yes, looking at, and with that, are you looking at adding new tanks assets? Are you looking at process augmentation, intensification, sorry, get my teeth in, technology, or no? So if you've got a comment on that, that would be great. Thank you. Okay. Thank you again for joining in with that. So we've got about 2/3 of people are involved with projects looking at growth, and about 1/3 aren't at the moment. So more of you are just looking at some potentially just phosphorus removal projects rather than the integrated growth challenge potentially and phosphorus. So thank you. That's great. So moving on to sort of a key part of the system for both CoMag and BioMag is the recovery of the magnetite, to maintain your magnetite in the system and not just let it disappear with your waste sludge. So here you've got a slide with a picture in the bottom right. You can see what looks like is a cutaway of the drum with some little squares. They're the magnets. So they're permanent magnets. They're not electrically wired. They're permanent magnets with a half-life typically of 200 years, 150 years, so, you know, far beyond the likely asset life of most things set on a wastewater treatment works. You can see just in the picture that basically it's 3/4. The magnetic array is in 3/4, and it sits fixed position from 12 till 9 o'clock, which you can see on the cutaway there, the dark grey band. So that is a fixed. And what actually rotates is a skin, like a stainless steel skin of a drum around the outside of that, and that rotates. So if I just move forward a little bit, so you have the ballasted waste sludge coming in on the right there. Now that's just prior to the entering the mag drum. It goes to something called a shear pump or shear mixer, which there's a sort of schematic of one there on above the mag drum cutaway. And that's an agitation process to break up the flocks, to try and help separate out the magnetite from the embedded flock in the CoMag technology and the BioMag. And that enables the recovery to be that much more efficient in the mag drum. So the ballasted waste sludge comes in that right port, having gone through the shear pump, shear mixer. We have the stationary magnetic array, which is between 12 and 9 o'clock. The outer screen drum rotates, and as it rotates, the ballasted sludge comes in. The magnetite obviously sticks by the draw of the magnets to the drum and is moved around anti-clockwise. As you can see by that arrow, it moves anti-clockwise as it's held by the magnets. And then as it gets to 12 o'clock, obviously the magnets aren't there anymore, and it becomes able to be removed from the skin of the drum, which occurs on the left-hand side. And then that is moved and scraped and with rubber scrapers against the drum into the recovered magnetite, which then drops back into your reaction tank 3 in case of CoMag, and in case of BioMag back into the magnetite makeup tank. Then the underflow, with the magnetite removed, is the waste sludge, and that goes on the underflow of the drum and then out through the port at the bottom. Hopefully that sort of gives you a view. So the technology CoMag and BioMag came from the States, came through Evoqua Technology, who bought the technology about 10 years ago. So it came into Xylem's realm when Evoqua were acquired 2.5-3 years ago. So there's a lot of references in the States, but I'm just focusing on the UK references, which have sort of really taken off in the last 6 years or so, 7 years, under the WINEP program and the challenge from P removal. So you can see there's a bit of color coding. The sort of, no, I'm slightly colorblind with some of these, so apologies. Lime green are the sort of early pilot trials, which I won't go into detail. We have a blue, which is Ruthin, Letty, Brongu, and Mosti. They're all CoMags, quite small flows, as you can see, on trickling filter works where we're utilising the existing humus tanks, and all we're fitting is some new reaction tanks. And then the light blue are all the CoMags, and you can see some quite large sites, like Nostrop is the largest globally with Blackburn Meadows at the moment. So Blackburn Meadows is around 4,500 litres a second. Nostrop treats around, we'll talk a bit more of that in detail in a minute. The first plant CoMag at scale that was built was Finham in Severn Trent, and we'll talk a little bit about that in a minute. And the first BioMag was at Rugby in Severn Trent. And these grey elements are BioMags. There's one in UU at Horwich, been operating for 3 years now as well. And then Burnley has just been commissioned and is online now. So you see there's quite a range, and there's quite a number now already in operation or in final stages. Some are in design for this AMP. We're looking at a few more. Finham. Part of the reason I want to show this was just to show the scale and the difference in size between ultimately a CoMag clarifier if you build new ones and your existing final tanks. So you can see a picture there, and you can see on the top right of the slide site of Finham is the large 12 final settlement tanks and the ASP lanes. There you go. So all the flow goes through the 12 ASP lanes, 12 final settlement tanks, and that gets then passed forward to where the CoMag plant is. So the effective area of the two CoMag clarifiers we've got here, which are two 75% capacity CoMag clarifiers, they're taking 150% of the flow that all those 12, potentially, all those 12. So the area it takes up is massively less. And then up front with the reaction tanks. And the reaction tanks here at Finham, part of the benefit for Severn Trent was that they had an old RGF plant, which basically they'd turned off after a year, hadn't operated for about 15 years. So it was an asset sat there just doing nothing. So we managed to reutilize the reaction tanks, reutilize the RGFs as the reaction tanks. So we converted some of the old RGF cells. So that was a great use for an old asset. They're not the ideal aspect ratios, because obviously there's certain aspect ratios of the reaction tanks in terms of height to width and length that you want to ideally have, and they're not perfect, but you know, they were good enough. So that was a great positive for the system. And the new clarifiers were built on the bed of old settlement tanks as well. So that was a sort of help as well. So you can see the sludge recycle and the sludge waste going back to the magnetite recovery system there. And the treated effluent disappears off to the river. So Nostrop, I briefly mentioned it before on the references. This is a site that was built in the last AMP on a largest works. Nostrop is Leeds. So it's treating 75% of the flow there, and they're using just one clarifier. So that's, and they're getting down to under 0.25. We can get lower, but they're blending. Their consent overall is 0.4. Great results. And here, if we look at some of the pictures from CoMag installations, it gives you a bit of context. The one in the center at the top, that is the Nostrop clarifier. So that's taking 75% of all the flow going through Nostrop. You'll see, which is typical for a lot of CoMag clarifiers, that we often need radial launders, which are the ones centered to the outer perimeter, and then the traditional peripheral launders. And that's just because the volume of the flow, you need more weir length to be able to discharge that liquid. The picture underneath is the two clarifiers at Finham. And as I say, typically most CoMag installations go down the route of utilizing 2 at 50% or 2 at 75% clarifiers, but it's down to the client's sort of requirements and requests. The picture at the top right is a silo, a magnetite silo. So as I say, that's tanker delivered and airlifted, blown into the top of the tank, and then it's fed, automated, and into the system. On smaller sites, we sometimes just have manual makeup systems for magnetite top-up. You can see on the top left there, magnetite recovery drums. So they're externally mounted. They don't need to be in a building. They're just on the access platforms. And the little picture, that's the little plant at Ruthin, where they had small stainless steel reaction tanks. And on the right is Leti Brungu, where we use the existing humus tanks on both those sites. And they're the reaction tanks, which are Forbes GRP type tanks, and we use them quite a lot. So a lot of sites have that concept. It's a bit of data on a site from Upper Gwynedd, not Upper Gwynedd in Wales, but in Welshwater. Sorry, in the US, Pennsylvania, rather than Welsh. And that just shows, as an ASP plant, that we're achieving very low ammonia. We're enabling the plant and the biology with its increased capacity to treat down to very low ammonia loads. And that was a question we've had on a number of plants, and that data is available through the EPA. And you can see it for all the BioMag sites in the States, how well they perform. In summary, BioMag CoMag can help you get down to very low. So 0.1 with CoMag, BioMag we say down to 0.25. You can utilize existing infrastructure both for CoMag with trickling filter works with humus tanks, and for BioMag, it's the concept is to use the existing tank assets. We have no backwash requirements on the clarification itself. We can do some parts of it as a modular build in terms of offsite. And And it can be combined, CoMag, as a tertiary stormwater treatment. That's what they're doing in Norway and have done in the States. So you get two benefits out of it potentially. Great. Thank you all for listening. I'll see if there's any questions come in. If you haven't, I'll kick off. I haven't seen any yet in the Q&A room, but a couple of things, sort of points on terms of things that get asked is the magnetite and the loss of magnetite. So it's about 1% on the CoMag system only, and that's typically that gets lost into the sludge line. There's no impact on downstream sludge treatment, and we have a number of sites and have done tests in the US. So there's no impact on your anaerobic digestion. It's an inert, so it just gets washed through the system as a solid. It's not like ferric chloride and what you dose as a coagulant, which can inhibit and has issues. It's totally inert. There's no impact downstream. And that's a question sometimes. So in BioMag, it's because of the grade, it's slightly harder to extract. So you're 95 to 97% recovery rather than 99. You do still need coagulant dosing, which is sometimes when people are unsure, but fundamentally you don't need as much, and that's with CoMag and you have a recycle line. So you're getting that contact time for longer. And typically we see sort of dose rates of down to sort of 5 to 8 milligrams per litre, depending on what the loading is coming in, etc. Which, from my experience of having dealt with other technology in previous lives, you know, you might be dosing at anywhere between 10 to 12 milligrams. So any step you can make in that direction is obviously beneficial in terms of ongoing running costs. If there's any questions, please put them in the Q&A. I haven't seen any others. Oh, there's some come in now. Sorry. That's great. So first question was, is there any benefit to the need to have both BioMag and CoMag on the same site? Typically, it doesn't happen very often. As I say, BioMag will give you a fairly good removal on the phosphorus challenge down to 0.25. So we haven't got any sites where we've got both fitted. I know it has been looked at in the States. There's a couple which they're actively looking at doing that, where they've had a BioMag and now looking at adding a CoMag. Derek asked the question, are there any other additional environmental concerns? Not particularly. If there's, you know, as I say, it's an inert product that in the sludge line where you lose some of it in terms of the magnetite itself. You're not introducing plastics or anything else. You're not a filter barrier that has microplastics. So I can't see anything else. You know, as you say, you're not totally getting rid of coagulants, ferric or alum. You still need to dose that like with other processes. In terms of another question from Nicholas, introducing this to an ASP, does this require higher oxygen requirement below demand? Typically, we find when we look at the design and BioMag with an ASP, there is a certain minimum mixing you require, but if it's a well-designed ASP system, we don't find you typically need much additional air to keep it mixed. The drive will come from the biology in terms of your BOD or ammonia removal, and you'll typically find that and its operation will enable it to keep mixed. But things like oxidation ditches, you know, you might need to review the flow mixers that you have in the tank are the correct to maintain a certain minimum velocity, and that'll be part of the modelling we do. In terms of humus tanks and the reuse, is there any special modifications we have to do? Fundamentally, no. We don't. As long as they're well maintained, you might have to do a bit of maintenance. So if some of the scraper blades on the bottom are failing and falling off, you know, we all know what these scraper systems are like after 10, 15 years, then you need to do some standard upgrade and maintenance. But typically, if there's a reasonable sidewall depth and reasonable aspect ratios, you won't have to do anything special to them. Because quite often with the CoMag, with the magnetite addition, the size of the humus tank is actually so much bigger than you really need that you know, the fact that it's not an ideal aspect ratio might not matter because you're actually dropping it out so quick. Okay, I think we're about at time. I'm sure my colleague Emily will tell me, but I think we're all there. I think we're up to 15:15. We're a bit beyond time. So thank you all for listening. That's great. And I really appreciate your time and joining me and Xylem on this sort of webinar. And I hope it's been useful. As I say, it will be made available to download and look at and share. I'd say I hope you've enjoyed this brief introduction to ballasted clarification and how it can be integrated into existing assets and how you can use some existing assets to support your challenge with P removal. If anything, you want to discuss anything, we are fully keen to collaborate and help you with your challenges and support you, looking at the options, looking at what it might do and what it can do to help you with the challenges moving forward that we have in the UK, particularly with AMP8, around both growth, capacity issues in our wastewater treatment works and P removal consent challenges. So thank you for your time and speak to you in the future, I hope. Thank you. Bye-bye.